Why, hello there. Welcome to 15 Minutes, the TV show about math IAs. Today we will be discussing Grace Hawes' IA. Today we'll go into the deep dive of the adventures of catnoids in space, black holes, and bubbles. So stick around. You might like what you see. Hello everybody, and welcome back to 15 Minutes with your host, Grace Hawes. Today we will be discussing Grace Hawes' IA. Hi, welcome Grace. Alright, so tell me your inspiration behind this IA. I'm so glad you asked me about my inspiration. So, what really inspired me was really thinking about math in a way that wouldn't be ever physical. It would mostly be theoretical. And I just really like that. There's a lot of appeal there, and I love the idea of just going into a thought and really deep diving into that thought and just working it out up in your head. As you know, I kind of struggled with picking with the topic. I went from statistics and law to climate modeling to magic statistics, and then I ended up in space. So it was truly something I was invested in after a while of searching. I'm so glad to hear that. Now let's get into the background of this project. What did you need? Well, I had a lot to do, so naturally I needed a lot of background. For example, at the time, I didn't know any calculus, and I needed to know about derivatives and how they would work with Euler-Lagrange's equation. I knew nothing about catnoids, and that's like a main thing in my project or investigation that I really needed to deep dive into and really learn about. In addition, I needed to learn about surface area, how it functions with different materials, such as, bubble solution, or, matter. So, yeah, the list goes on and on for what I did background on. That is an interesting point you make. Hey, we'll come back to discuss more on this and what she went through after this commercial break. Has this ever happened to you? You're trying to do theoretical math and you need a hyperbolic function? Not to worry. Just isolate cosine x from the rest of Euler-Lagrange's equations to get a hyperbolic function with imaginary numbers. Take out the imaginary numbers, and what do you got? What do you got? That's right, hyperbolic functions. How do hyperbolic functions help you? Well, when you're looking at a catnoid, like you do, you then need hyperbolic functions to determine surface area. And that's up. That's what's up. So if you need Euler-Lagrange's hyperbolic functions to get hyperbolic functions, just call this number below. Welcome back. Today, as you know, we are discussing Grace Hawes' IA. So tell us a little bit about bubbles and how they played a role in your IA. Well, actually, bubbles are really, really interesting because they're incredibly specific about how their surface area works, especially when put into a catnoid's shape. So a catnoid shape it has two rings at the ends, and it goes in sort of like I'm at a loss for words. The timer that you get at the dentist's. It's similar to that shape. So, as you can see, bubbles are very delicate, and they'll pop if you touch them, obviously. And so bubbles are special because at all times the surface area of a bubble needs to be the least as possible. So when this creates like a really awesome experiment because with the two rings, if you get some bubble solution, it'll create this catenoid thing. And as you pull the rings apart, the surface area gets stretched and stretched and stretched. And to maintain the surface area, the radius in the middle of the catenoid will get smaller and smaller and smaller. So on a graph, it would go up and then it would go down because it's just getting smaller and smaller and smaller. Until you get to the popping of the bubble where the radius is 0, and then it turns back into 2 bubbles, and then the surface area increases again because it goes from 1 to 2. And then it decreases again because as it goes into the rings, it's a shorter surface area. So it's kind of like a wave, sort of. Yeah. So this shape is a catenoid, and it's very important for my experiment, or my investigation, because it's really the basis of a wormhole. A wormhole is a place or a thing in space, potentially, theoretically, where 2 holes in space and time meet, and it's sort of like if you folded a paper over and stuck a pencil through it. That would be a wormhole. Instead of traveling the whole distance of the paper, you go through the hole. It's much faster. And theoretically, these wormholes could be acting the same as a collapsing catenoid in the bubbles. Well, that's not all, folks. We still need to connect to space, and we will, right after this break. What's up, everybody, and welcome to Math Today. Today, we're going to be performing a bubble experiment. This will mimic a catenoid collapsing. So what you're going to do is you're going to put 2, like, bubble thingies together, like that. Keep them real close together, and dunk them in at the same time. Then record yourself and watch in slow-mo as the bubbles pull apart like a catenoid. What would be the purpose of this? Well, that's interesting that you say that. If you keep watching 15 minutes with Grace Hawes, then not to worry. You'll learn all about it. But to calculate the surface area, you're going to need my product, hyperbolic functions. When you get hyperbolic functions, you can calculate the surface area of these guys. So, call now to get those hyperbolic functions in your inbox. Thanks, homie. Hi, welcome back. Today, we're going to be discussing Grace Hawes' IA. And tell me a little bit about how you connected this bubble with space. So, to connect these guys, we first need to take a look at black holes. Black holes are really interesting because they have a ratio of mass to radius, and it's really, really integral to keeping the structure of a black hole. If it's not enough mass in a black hole, it's not actually a black hole. So basically, for one of the Earth's mass, it for it to be a black hole, it would need to have the radius of 0.88 centimeters. So, like, this big. That would have to be the entire Earth's mass. So, obviously, these things are very heavy, and they're, like, infinitely heavy. So, they kind of mirror the bubble in the catenoid shape that, they have a hole at one end, and then this is the part where the theoretical parts come in, and if we assume that there's another hole in the singularity, which is at the end of the black hole, then we can assume, or that I can assume from what I've learned about bubbles and the catenoid shape, that it makes a catenoid shape and it may collapse. So yeah, if stretched far enough apart, if the singularity and the the horizon of the black hole gets far enough apart, it could collapse. Who knows? Interesting. How can you know this is all true? So, as I said before, this is all hypothetical, assuming that there's such things as wormholes and that there actually may be a singularity at the black hole with something like across it. And there may be, but it's all speculation. But it's kind of nice to think, hey, maybe if there's these things in space, then we can mirror them on Earth with things we know, like bubbles. And I think that's just really interesting and cool about the world. Well, that is just lovely. I'm afraid that's all the time we have today. And I would like to thank everyone who helped Grace with her IA and who helped with the show. So let's send Grace off. Bye. Funding for the show is thanks to IB Math Class 2021 with Aaron Hall, and thanks to Theoretical Math. Your sponsorship is wonderful, and we appreciate it every day. Stay tuned for more IA projects later on today. Thank you. Bye-bye. What's up, everybody? This is Math Help Today, coming to you with some quick math help, because there may or may not be a question on my part of the quiz that's asking you for some information. Let's get into it. So, if you'll recall, when you have a graph and you have a line, to find the slope of this line, you do rise over run. So, cool. So, basically, what you do is you take 2 points on the graph, one here, on the line, and you do y1 minus y2, or vice versa, over x1 minus x2, or vice versa. These guys just have to match. And then that's how you get slope. To find the y-intercept, all you have to do is plug in 0 for x. With that, then you get the y-coordinate, which would be the y-intercept. And that is how you get your function of rise over run. And intercept m equals mx plus b. Y equals mx plus b. So, try it out, either right now, or if he picks that question for the final, then try it out and have a good time.